Demand factors are used in electrical calculations to account for the fact that not all electrical loads operate at their maximum capacity at the same time. This allows for a more accurate determination of the total load on a service, feeder, or branch circuit. The National Electrical Code, or NEC, provides tables and guidelines for applying demand factors to various types of loads. The note that says select one demand factor is likely referring to the case where there is a single load that is made up of multiple types of loads. It is possible to use multiple demand factors for a single load when there are multiple types of loads connected to the service. The key is to understand the composition of the load and apply the appropriate demand factors to each component. For example, consider a scenario where there is a 300 kV load. This load is composed of two distinct parts: firstly, a 200 kV heating load, and secondly, a 100 kV lighting load. The heating load has a demand factor of 0.8, indicating that it's expected to operate at 80% of its maximum capacity. The lighting load has a demand factor of 1.0, meaning it's expected to operate at full capacity. To calculate the total demand factor for the 300 kV load, apply the demand factor to each component and then divide by the total load. The calculation is as follows: total demand factor equals 0.8 multiplied by 200 kV plus 1.0 multiplied by 100 kV, all divided by 300 kV. This results in a total demand factor of 0.867. In contrast, consider a scenario where there is a 348 kV load that is all electric. In this case, it is appropriate to use a single demand factor of 1.0 for the entire load. This is because the entire load is of the same type, all electric, and there is no need to differentiate between different components with varying demand characteristics. When dealing with multiple types of loads, it is necessary to select a single demand factor that represents the overall load. This is typically done by weighting the demand factors of each component by its proportion of the total load. The NEC provides tables that list demand factors for various types of loads, such as lighting, heating, cooling, and appliances. These tables can be used to determine the appropriate demand factors to apply to each component of the load. It is important to note that the NEC specifies when and how demand factors can be applied. Always refer to the latest edition of the NEC for the most up-to-date information and guidance. Understanding demand factors is crucial for accurate electrical calculations and for ensuring the safe and efficient operation of electrical systems. By applying demand factors correctly, it is possible to reduce the size of conductors, overcurrent protection devices, and other electrical equipment, which can save money and improve the overall efficiency of the system. In the example of the 300 kV load consisting of 200 kV of heating and 100 kV of lighting, the heating load's demand factor of 0.8 suggests that not all heating elements will be operating at maximum capacity simultaneously. This could be due to thermostatic control, occupancy patterns, or other factors that limit the concurrent usage of the heating equipment. The lighting load's demand factor of 1.0, on the other hand, indicates that all the lighting fixtures are expected to be on at the same time. This might be typical in a commercial building or a residential setting where lighting is used extensively during certain hours. When calculating the total demand factor, it is essential to consider the specific characteristics of each load component and apply the appropriate demand factor based on its anticipated usage pattern. This approach ensures that the electrical system is designed to handle the actual load demand rather than being oversized based on the maximum potential load. For the 348 kV all-electric load, the use of a single demand factor of 1.0 implies that all the electrical equipment is expected to operate at full capacity simultaneously. This might be the case in an industrial facility or data center where continuous operation of all equipment is critical. In such scenarios, it is prudent to design the electrical system to handle the full load demand to ensure reliable and uninterrupted power supply. The NEC provides detailed guidelines on how to apply demand factors to different types of loads. These guidelines are based on extensive research and field experience, and they are intended to ensure the safety and reliability of electrical systems. When applying demand factors, it is crucial to carefully consider the specific characteristics of the load and the anticipated usage pattern. This requires a thorough understanding of the electrical equipment, the building occupancy, and the operational requirements. In some cases, it may be necessary to consult with a qualified electrical engineer to determine the appropriate demand factors to use. The use of demand factors can significantly impact the sizing of electrical equipment and the overall cost of the electrical system. By applying demand factors correctly, it is possible to reduce the size of conductors, overcurrent protection devices, and other electrical equipment, which can save money and improve the overall efficiency of the system. However, it is important to note that demand factors should not be used to intentionally undersize electrical equipment. The electrical system must be designed to handle the actual load demand, even if it is less than the maximum potential load. In addition to the NEC, there are other industry standards and guidelines that provide information on demand factors. These standards may be specific to certain types of loads or industries. It is important to be aware of these standards and to use them in conjunction with the NEC when applying demand factors. Demand factors are an essential tool for electrical engineers and designers. By understanding and applying demand factors correctly, it is possible to design safe, efficient, and cost-effective electrical systems. Remember to always consult the latest edition of the NEC and other relevant industry standards for the most up-to-date information and guidance. The goal is to optimize the electrical system design based on realistic expectations of load usage, ensuring both safety and efficiency. This involves careful consideration of the types of loads, their individual demand characteristics, and the overall operational profile of the facility or building. In cases where a load is composed of diverse components, such as heating, lighting, and motor loads, it is crucial to analyze each component separately and apply the appropriate demand factor based on its specific characteristics. This approach allows for a more accurate assessment of the total load demand and prevents over or undersizing of electrical equipment. For example, in a commercial building, the lighting load may have a higher demand factor during peak business hours, while the heating or cooling load may have a lower demand factor during off-peak hours. By considering these variations in load demand, it is possible to optimize the electrical system design and reduce energy consumption. In industrial facilities, motor loads may have varying demand factors depending on the type of equipment and its operating cycle. For instance, a continuously operating pump may have a higher demand factor than an intermittent use conveyor. By analyzing the operating characteristics of each motor load, it is possible to determine the appropriate demand factor and design the electrical system accordingly. The NEC provides specific guidelines for applying demand factors to various types of loads, including lighting, heating, cooling, motors, and appliances. These guidelines are based on extensive research and field experience and are intended to ensure the safety and reliability of electrical systems. When applying demand factors, it is important to carefully consider the specific characteristics of the load and the anticipated usage pattern. This requires a thorough understanding of the electrical equipment, the building occupancy, and the operational requirements. In some cases, it may be necessary to consult with a qualified electrical engineer to determine the appropriate demand factors to use. The use of demand factors can significantly impact the sizing of electrical equipment and the overall cost of the electrical system. By applying demand factors correctly, it is possible to reduce the size of conductors, overcurrent protection devices, and other electrical equipment, which can save money and improve the overall efficiency of the system. However, it is important to note that demand factors should not be used to intentionally undersize electrical equipment. The electrical system must be designed to handle the actual load demand, even if it is less than the maximum potential load. Demand factor application necessitates a clear understanding of the NEC guidelines, load characteristics, and operational considerations to ensure the safety, efficiency, and reliability of electrical systems.